What specific problem does your method aim to solve related to model distillation? And why is this problem significant in the context of natural language processing?
Our method aims to address the critical gap in understanding how model distillation modifies the reasoning capabilities and feature geometry of distilled models compared to their base counterparts. Specifically, we investigate the distinctive features that distilled models develop, the relationship between model size and the number of unique features, and how the feature geometry changes as a result of distillation. This problem is significant in the context of natural language processing because it contributes to improving the transparency and reliability of AI systems, which is essential for building safe and robust models. By elucidating the unique reasoning features and structured representations that emerge through distillation, we can enhance the performance of smaller models, making advanced capabilities more accessible and efficient. Ultimately, this understanding can lead to better designed models that are capable of complex reasoning tasks, which is crucial for advancing the field of natural language processing.
How does the proposed method work? Illustrate the step-by-step process of training the sparse crosscoder and how it facilitates the identification of unique features in distilled models.
The proposed method involves training a sparse crosscoder to identify unique features in distilled models. First, the crosscoder is trained using activations from two models, referred to as Model A, the base model, and Model B, the distilled model, by computing the crosscoder feature activation based on their respective activations at specific tokens. The training minimizes a loss function that combines reconstruction mean-squared error, MSE, and the L1 norm of the decoder vector. After training, the relative decoder norm, RDN, is calculated to differentiate between shared and unique features, where an RDN approaching 0 indicates features unique to the base model, and an RDN approaching infinity indicates features unique to the distilled model. By analyzing the distribution of these norms, the method successfully identifies reasoning features unique to the distilled models, such as self-reflection and verification reasoning, thereby elucidating how distillation modifies model capabilities.
Can you provide a simple yet illustrative example that showcases the inner workings of your proposed algorithm, particularly focusing on the extraction of unique reasoning features?
An illustrative example of the extraction of unique reasoning features using our proposed algorithm involves the analysis of self-reflection reasoning in distilled models. We trained a sparse crosscoder on activations from distilled models, such as DeepSeek R1 Distill Quen 14b, to identify features unique to these models. For instance, we observed that the self-reflection feature, which activates on the token weight, allows the model to recognize potential errors in its reasoning process and correct itself. By measuring the normalized relative decoder norm, NRN, we found that this feature is unique to the distilled model, as indicated by an NRN value close to 1, while the base model did not exhibit this capability. This demonstrates how our algorithm effectively extracts and quantifies unique reasoning features that enhance the model's performance in complex problem-solving scenarios.
What are the theoretical or practical benefits of using the sparse crosscoder approach compared to traditional methods of analyzing LLMs?
The sparse crosscoder approach offers several theoretical and practical benefits over traditional methods of analyzing large language models, LLMs. Firstly, it enables the examination of interactions between different activations from various models, layers, or context positions, allowing for a more nuanced understanding of how features are shared or unique across models. This is particularly useful in identifying distinctive features that contribute to reasoning capabilities, as demonstrated in the analysis of distilled models. Secondly, the crosscoder's ability to reconstruct activations facilitates the quantification of feature norms, providing insights into the geometry of features and how they evolve through processes like distillation. Additionally, the sparse crosscoder can effectively highlight causal relationships between features and model behavior, as evidenced by the ablation experiments that showed significant logit changes in distilled models compared to base models. Overall, the sparse crosscoder enhances interpretability and transparency in LLMs, contributing to the development of more reliable and robust AI systems.
How was the effectiveness of the sparse crosscoder validated or tested? Describe the datasets and metrics used to evaluate its performance and compare it with the base models.
The effectiveness of the sparse crosscoder was validated by training it on two datasets, one containing math, science, and code reasoning traces generated by the DeepSeek R1 model, and another comprising general text from the Hugging Face dataset. Specifically, 200 million tokens from each dataset were utilized to identify both reasoning and general text features of the models. The performance of the sparse crosscoder was evaluated using the relative decoder norm, RDN, and normalized relative norm, NRN metrics, which help distinguish shared features from those unique to the distilled models. The analysis revealed that larger distilled models, such as Qwen 14b, exhibited a greater number of unique features compared to smaller models, indicating that the crosscoder effectively captured the differences in feature geometry between distilled and base models. Additionally, ablation experiments demonstrated that the reasoning features identified by the crosscoder were causally responsible for improved reasoning capabilities in distilled models, further validating its performance.
What specific results did you achieve with the sparse crosscoder when analyzing the reasoning features? What insights did these results provide about the distilled model's capabilities?
Using the sparse crosscoder, we identified unique reasoning features in distilled models, such as self-reflection and verification reasoning, which were not present in the base models. The analysis revealed that most features were shared, but larger distilled models exhibited a greater number of unique features, particularly in the 14b model, indicating a correlation between model size and reasoning capabilities. We conducted ablation experiments that demonstrated the causal relationship between these reasoning features and the distilled model's performance. The logit changes in distilled models were significant upon feature ablation, while base models showed minimal changes. Additionally, we observed that distilled models could be steered into different thinking modes, such as overthinking and incisive thinking, showcasing their enhanced reasoning flexibility. Overall, these results suggest that distillation not only introduces unique reasoning capabilities, but also improves the structured representation of knowledge in larger models.